So 6.5, we're dealing with factoring binomials. So real quickly, our formula is if we have something squared plus or minus something squared, the way that factors is we take whatever's being squared there minus whatever's being squared there. And then we do the same thing with the plus in the middle. So that's just a formula that allows us to factor. This is called a difference of squares. Something that is a square minus something that's a square. That formula always works. If we were to square this out, notice the first, a times a makes a squared. The last makes minus b squared. But if we combine the outer and the inner product is negative b times a, or we could call that minus ab. The outer product is positive a times b, and those cancel. So we would end up with a squared minus b squared. So yes, this does work to factor a squared minus b squared. If we have a sum or difference of cubes, the difference of cubes factors into whatever's being cubed minus whatever's being cubed, and then we have the first one squared, we have this times that, and then we have the second one squared. If we have a sum of cubes, then our formula is a plus b, so whatever is being cubed plus whatever is being cubed, and then the first one there squared minus the first one times the second one plus the second one squared. And as we work several examples out, we'll see in more detail how those formulas work. Notice that these are almost exactly the same. If you can remember the terms, there's an acronym, SOAP, that'll allow us to determine what our signs are. The first sign is the same as what we're factoring. If it's a minus, that's a minus. If it's a plus, that's a plus. The next sign is the opposite of what we start with. If this is a minus in the middle, that's a positive. If this is a positive, that's a negative, so the opposite. And notice in both cases, the last sign is positive. So the last sign is always positive. So instead of completely memorizing the whole thing, you can figure out what your terms are, and then this acronym will tell us what signs go where. So that's just a little trick that we'll use to factor these eventually. So the one we have here, this example is a difference of squares. The first term is x that's being squared. The second term is 5 that's being squared. So it's a difference of two squares. So the way we factor that is we're going to have two parentheses. Whatever is being squared minus the other thing that's being squared. Or another way of saying it is our base minus our base. And then the same terms with a plus in the middle. If you were to distribute that out, the outer and the inner would cancel, and we would be left with the x squared and the minus 25. So these are a little bit different than the ones we've done previously. These more utilize a formula than anything. If we look at this one, this is also a difference of squares. So let's take each term and write it as something squared. So 25 is 5 squared. That is x squared. And 64 is 8 squared. 64 is 8 times 8. So since we have something that's squared minus something else that's squared, then this is going to factor into two parentheses. The first base minus the second base, and then those same terms with a plus in the middle. Now technically it doesn't matter which parentheses we put the plus in and the minus. as long as one of them is positive, one's negative. So those are the same. And the next one, we can do this a couple of ways. Typically, we do like to have our variable term first, but we like to have our leading coefficient to be positive. So if our leading coefficient is negative, one thing we could do is factor out a negative, or you could say a -1. 1 goes into everything however many times we have. So, for example, 169 divided by 1 is still 169. When we factor out a negative, it just changes the sign. 1 goes into 1 one time, but if we factor a negative, it changes the sign. Notice if we were to distribute that negative, we would get these signs. So now on the inside of that parenthesis, that's the difference of squares. 169, make room to write this. 169 is a perfect square. It's 13 squared, and then we have r squared. And then 1 is also a perfect square. 1 is 1 times itself. So, since we have something squared minus something squared, it's the first base minus the second base, and then the first base plus the second base. And then we bring down the -1 that we factored out already. So once we recognize what's being squared and what's being squared, we just bring the bases down with a minus and then with a plus. And again, I would encourage you to distribute those, multiply those out as a check, just to see that this really does work and how it works. This one, we could factor a negative out, or we could just rearrange it. We could have rearranged the other one so that the first term was positive. We did it differently, but we could rearrange this one. Notice the first term is positive, the second is negative. We could have factored out a negative here and made the first term positive that way, but normally we like to have our leading term to be the variable term. So this is the difference of squares. It's something squared minus something squared. X squared is x to the second power, and 81 is 9 to the second power. So since it's a difference of squares, again, our two parentheses is our first base minus our second base, and then those two added together. In terms of the way we did it back in section 2, you could say this comes from the first, so x times x. This comes from the last, so -9 and 9. Since the middle term doesn't exist, the middle term has to make 0. So what numbers multiply to make -1 and add to make 0? Well, -9 times 9 makes -81. -9 plus 9 makes 0, so that's why we don't have a middle term. But to a lot of us, that's a little confusing, so no need to think of it in that connotation. Now let's look at this one. We don't see something to the second power. We don't see x to the second or m to the second here. But this still is a difference of squares. If we have m to the fourth, and we want to write that as something squared, remember if we have an exponent here and an exponent here, the way those get combined is they get multiplied together. This exponent times that one. So what would our exponent here need to be so that when we multiply those exponents, we make 4? Well, it would need to be a 2. So m to the fourth can be written as something squared. That something just happens to be that. So it's something raised to the second power. 16 is 4 to the second power, and 625 is 25 to the second power. You might be like, well, I don't know that. You could take your calculator and you could do 625, take the square root of it. That will tell you what number squared makes 625. So now that we have written this in terms of two squares, a difference of squares, then we write our two parentheses. What's being squared here minus what's being squared there. And then those same terms with a plus in the middle. Now, we're actually not done because one of these factors can be broken down farther. What do I mean? Look at the first one. 4 is something squared, that's something squared, and that's something squared, and we have a difference. So that first parenthesis is also a difference of squares. So what squared makes 4? 2. What squared makes m squared? Well, m. And what squared makes 25? 5. So we would have 2m minus 5, 2m plus 5. Notice 2m times 2m is 4m squared, 5 times 5 is 25. Now the second parenthesis actually doesn't factor. It turns out that if we have a sum of squares, we don't have a formula to factor a sum of squares. So if it doesn't fit some other category that can be factored, a sum of squares is prime. So that's as far as we can go. None of those parentheses now will break down any farther. Now the next category we have is dealing with the cubes. So this one is not a sum or difference of squares. Notice we have an x to the third. But 48 is not something to the third power, neither is 6. So that brings up a dilemma. But notice those two terms have something in common. Both of those terms are divisible by 6. We always pull out common factors before we do things more complicated. So the first term is 6 times x cubed. The second term is 6 times 8. So we factor out our common factor and put it in the front. Now what's left inside, that's the sum of cubes. I'm just going to come over on the side for now. The first term is x that's being raised to the third power, and 8 is 2 to the third power. 2 times 2 is 4. 4 times 2 makes 8. So each of those are something to the third power. So if we were to go back and look at the formula that we wrote on the first page of factoring a sum or difference of cubes, once we find out what's being cubed, we bring the first base down and the second base. And that tells us what goes in the first parenthesis, just like we did with the squares, the base and the base. After we figure out what's being cubed, then for the next parenthesis, the first term comes from taking this one and squaring it. So x squared. Notice x times x squared, if we were to distribute that, x times x to the second would make x to the third. The term on the other end comes from doing the same thing with a 2. That last term comes from squaring a 2. Which 2 squared, of course, is 4. Notice that this number times that number makes 8. But we also have another term that goes in the middle here. And that term comes from multiplying these two together. So x times 2 would give us a 2x in the middle. And then we use the acronym SOAP to get our signs. The first sign that we need is the same as what we started with. The next sign that we need is the opposite of what we started with, and then that one's always positive. So we end up with x plus 2 times x squared minus 2x plus 4. Now, I would encourage you to distribute that as a check to make sure that this really does work, because that's a really messy formula. Where did all that stuff come from? But we're going to use that same formula each time we have a sum or difference of things that are being raised to the third power. So again, we take this base, bring it down, take this base, bring it down, take the first base, square it, take the second base, square it, and then in between those, we get their product. So quickly as a check, if we distribute x times x squared is x to the third, x times minus 2x is minus 2x to the second, x times 4 is 4x. 2 times x squared is 2x squared. 2 times minus 2x is minus 4x, and 2 times 4 is 8. Notice those cancel, leaving us x cubed plus 8, which is what we were factoring. So yes, that formula really works. So x cubed plus 8 factors to x plus 2 times x squared minus 2x plus 4, and we bring our 6 down. So that's how we're going to factor that one. This next one is also cubes. So we want to see what cubed minus what cubed. So the first term is q being cubed and r being cubed. And 64 is actually 4 to the third. It's good to have a working list of numbers that are perfect cubes. And we don't have to have a very long list, but 1 to the third, 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 64 and 125. Those are some fairly common perfect cubes that we come across. So 64 is 4 to the third. So now that we know that that term and that term are both things that are being raised to the third power, then we can write our two parentheses. So we bring our first base down, and we bring our second base down. The next parenthesis has 3 terms. The first one comes from taking the first term here and squaring it. So if we square that first one, we get q to the second, r to the second. The last one comes from squaring the other term, so 4 to the second. 4 times 4 is 16. And the middle one comes from multiplying the two bases. QR times 4, so that would be 4QR. And then SOAP. The first sign is the same, the next one is the opposite, and the last one is always positive. So that gives us what we were trying to factor there. Here we have another. This is a sum of cubes. This is n being raised to the third. And 64 again, that's 4 to the third. So we're going to have two parentheses, our first base and our second base, and then for our 3 terms, the n squared, the 4 squared, and then the n times 4. So the first one is just n squared, the next one is 4n, and then 4 squared is 16. So SOAP, the first sign is the same, the next sign is the opposite, and then always positive. And again, that's in reference to this sign. The same sign, that's the opposite, and then the last one is always positive. Here, this one can be a little tricky because we do have a cube there, but remember we always look for common factors first. Both terms have an s in common. So if we have s to the third and we pull a common s out front, we're left with 2 on the inside. If we have 25 times s and we pull the s away, we're left with a 25. And both of those are squares, but we mentioned earlier if we have squares that are added, that's not factorable. We don't have a way of factoring sums of squares. So that's as far as we can go with this one.